Measures of dispersion. So we've been studying measures of central tendency. Remember, averages like the mean and the median, the mode, the mid-range. Those are measures of central tendency. But measures of central tendency by themselves don't always give sufficient information to analyze a situation and make really good decisions. So it's going to be so important for us to know something about the spread or variability of the data. So in this lesson, we're talking about two measures of variability or measures of dispersion. Measures of dispersion are used to measure the variability of the data, including the spread of the data, and how the data vary about the mean. So two measures of dispersion that we'll look at are the range and standard deviation. All right, let's start with range. Here's the definition for range. It is the highest value minus the lowest value. The amount of calories in a slice of cheese pizza from 9 different brands are given. Determine the range of this set of data, or these data, because data could be plural, right? All right, according to our formula here, we take the highest value and we subtract from it the lowest value. Now, the highest value is 320 and the lowest value is 234, which gives you a difference of 86. So it's that simple, folks. The range is 86. Let's talk about standard deviation. Standard deviation measures how much the data differ from the mean. Now, when we write standard deviation, either we use the letter S or the Greek lowercase letter sigma, which is like that. I probably did a poor job, but this is kind of like the lowercase Greek letter sigma. S is used when standard deviation of a sample is calculated, and sigma is used when the standard deviation of the entire population is calculated. Since we are assuming that all data presented here are for samples, we're going to use S, okay? The English lowercase s to represent standard deviation. What's important for us to note is that the larger the variability of the data about the mean, the larger the standard deviation. For example, both of these sets of data have a mean of 9.5, okay? Both of them. But which set of values do you think differs less from the mean? Look at this picture. This graph here shows how the values in this first set here differ or vary from the mean. The data is really spread out, if you will, from the mean. Compare this to the following graph. Look at how the data does not vary that much from the mean compared to the previous set. You know what I mean? So because these values here vary less from the mean, this set here is going to have a smaller standard deviation. All right? So many times only a very small standard deviation is desirable or acceptable. All right? At other times, a larger spread of data is desirable or expected. All right? So here we go. Let's look at how we are going to determine the standard deviation of a set. Okay, these steps can be followed for finding the standard deviation of a set of data. All right? So we're going to jump into an example here that illustrates this procedure. All right? So let's go for it. A veterinarian in an animal hospital recorded the following lifespans of selected Labrador retrievers. This is to the nearest year. So 7, 9, 11, 15, 18, and 12. Determine the standard deviation of the lifespans. All right, the first thing we need to do is determine the mean. Remember, this is our notation for the mean, okay? It is the sum of all the data divided by the number of pieces of data, right? So then it is 7 plus 9 plus 11 plus 15 plus 18 plus 12, okay? All divided by 6, okay? So this is 72 over 6. So the mean is 12. The next thing we're going to do is we're going to make a table with 3 columns, okay? All right, we have our 3 columns, data, and then the difference between the data and the mean, and then the square of that difference. All right, let's list all of our data here. All right, we have all of our data. Now we need to subtract the mean from the data. So in this case here, we need to do 7 minus 12. That difference is -5. Next, what we're going to do is we're going to take this difference, -5, and we are going to square it. Be careful with your notation here. Because you're squaring a negative value, you must use parentheses here. Please do not write this -5 squared like this. This actually is interpreted as the opposite of 5 squared. So 5 squared is 25, and the opposite thereof is -25. So if this is your notation, you're actually squaring +5 and negating the result. Whereas this notation, because parentheses are used, you're squaring whatever's inside the parentheses. So you're squaring -5. Because no parentheses are being used here, you're squaring +5. So just be a little word about notation. Okay, so we need to do this for each one of these pieces of data. So next is going to be 9 minus 12, and then 11 minus 12, and 12 minus 12, and so forth. All right, I have all of these differences. Again, this is all of the pieces of data minus the mean. Now I need to take these differences, like I did -5, and I need to square all of them. All right, I just squared all of them. Please note my notation. I did use parentheses here because I'm trying to square -3, which is -3 times -3, of course. And then -1 squared, I'm squaring -1, so I have to use parentheses. So -1 times -1, which is +1. 0 squared, of course, is just 0 times 0. Notice that the base of my exponent is positive. The base of my exponent before is negative. The base is -3. The base is -5. But this base, 0, there's no negative. This base here is +3. This base here is +6. Whenever your base is positive, you don't need parentheses. Now, you can use parentheses every single time, right? But whenever the base is positive, you don't need parentheses. But if the base is negative, you absolutely need parentheses. I'd like to draw your attention to something here. Let me see if I can move this up. If you have done this correctly, then the sum of all of these differences should be 0. -5 plus -3 is -8. -8 plus -1 is -9. -9 plus 0 is -9. -9 plus 3 is -6. And -6 plus 6 is 0. So when I sum all of these differences, I get 0. Now, if you've done this correctly, you should get 0. If you don't get 0 when you add all of these differences, something's wrong. Now, but keep in mind, if you're using a rounded value, a value that's been rounded, so an approximation for x bar, remember x bar, our mean is 12, right? This difference here is this value is your mean, right? 12, that's an exact value. But if you use an approximation for your set of data for the mean, then this sum, the sum of all these differences, may not be 0 because you use an approximation for x bar. But it should be really, really close to 0, okay? So if x bar, okay, if the mean is an approximation, then, okay, the sum of these differences may not be 0, but it should be really, really close to 0. If you use an exact value like I did, the mean is exactly 12, then notice that the sum of these differences is 0. All right, so just keep that in mind, that this sum right here should be exactly 0 or really, really close to 0 if x bar is an approximation. All right, the next thing to do, according to our steps, is to add the squares, all of these squares in this column. Let's do that. Let's do 25 plus 9 plus 1 plus 0 plus 9 plus 36. All right, and we get 80. What we need to do next is we need to divide this sum. We need to divide 80 by 1 less than the number of pieces of data. Remember, we wrote it as n minus 1. Okay, so what I'm going to do is I'm going to take this number 80 and I'm going to divide it by n minus 1. Remember, n represents the pieces of data, the number of pieces of data. In this case, which is 6, right? So then it's 6 minus 1. In other words, we're dividing the sum 80 by 5, and we get 16. Now, this number 16 actually has a special name. It's actually called the variance of the set of data. You may want to add that to your notes. This number 16 is the variance, meaning it is the square of your standard deviation. Remember S stands for standard deviation. And so this number is the square of the standard deviation, called the variance. Okay, the last step is to take the square root of our variance, square root of this number that we got here. So let me just move this up a little bit. All right, so now I'm taking the square root of the variance, right? Square root of 16, which is 4. Therefore, the standard deviation, which we use S to represent, is 4. I'm just going to box that as our answer. This is the standard variation. Now we can develop a formula for finding the standard deviation, so you don't have to follow all of those steps necessarily. So notice that the first thing we did is we found the mean, right? And then once you found the mean, we subtracted the mean. So this is the first thing we did, found the mean. And then the next thing we did is we subtracted the mean from each piece of data. We subtracted that from each piece of data. And then we squared that difference, right? And then we took this sum. We found the sum of all of those squares. Remember, that was 80. And then we divided that sum, which is 80, by n minus 1. And then we took the square root, so this is the variance right there. Before the square root, this is the variance, which in our example was 16. And then we took the square root of this, and this here is the standard deviation. So this, folks, you may want to highlight this or box this. This is the formula for the standard deviation of a set of data. All right, let's look at a new example and find the standard deviation. All right, the following are the prices of 9 stocks on the New York Stock Exchange. Determine the standard deviation of the prices. All right, so we got $17, $28, $32, $36, $50, $52, $66, $74, and $104. All right, first things first, let's find the mean, X bar. All right, so this is the sum of all the data divided by the number of pieces of data. So 17 plus 28 plus 32 plus 36 plus 50 I'm writing sloppily, sorry, plus 52, plus 66, plus 74, plus 104, right? All divided by 9. So this gives us 459 over 9, which is 51. So 51 is our mean. $51 is our mean, all right? Now, let's create a table. My table is going to look just a little bit different, okay? All right, so instead of writing the word data, I just put X, okay? Instead of writing data minus mean, I just put X minus X bar. Instead of writing data minus mean quantity squared, I just wrote X minus X bar quantity squared. That's what I meant by my table looks a little different. Instead of writing words, I used our symbols. All right, so let's list all of our data. Here, let me leave this like that. All right, cool. All right, I have all of my data values, and now what I need to do is subtract from each one of these values my mean. Remember, the mean is 51, so I need to do 17 minus 51. I need to do 28 minus 51. I need to do 32 minus 51, and so forth. And put those differences here. All right, here are those differences. Remember that if we did this correctly, the sum of these differences must be 0. And it is. If you take the time right now to, and I invite you to do this, if you add up all of these numbers, you actually get 0. That tells me I'm doing something correctly, all right? Remember that if X bar is an approximation and not exact, in this case, our X bar is exact, it's 51, right? But if your X bar is an approximation, then the sum of these differences should be really, really close to 0. In this case, it is exactly 0 because my X bar value, 51, is exact. Okay, the next thing I do is I square all of these numbers, negative 34 squared, negative 23 squared, negative 19 squared, and so forth, and put these squared values here in this column. All right, I have all those squared values. Remember, what I need to do next is sum all. I'm at this step right here, folks. So sum. I need to sum all of these values. Let me move this up. All right, I have my sum. Again, that was this part of the step of the formula. So the next thing I need to do is take this sum, 5,836, and I need to divide it by n minus 1. Because there are 9 different stocks, 9 different data values, n minus 1 in this case is going to be 9 minus 1, which is 8. So actually, let me write it like this. My standard deviation, which is S, right, is equal to the square root of all of this, right? And so now this is the square root of, I know what the numerator here is, it's 5,836. And I'm dividing that by 8, 9 minus 1, right? So this is the square root of 729.5, which is approximately equal to 27.01. Now, in this context, in the context of this problem, we're talking about money, right? Dollar values. And so therefore, don't forget your unit, right? Your units are dollars, right? So this is $27.01. Of course, we rounded to the nearest hundredth. They never told us to, but we need to know that we need to round to this place value. Why? Because we're talking about money. So we're rounding to the nearest hundredth or the nearest cent in this case. All right. So because it's money, we should know we need to round to the nearest cent or the nearest hundredth. All right, folks, $27.01 is the standard deviation for this set of data. Great job.